Amazing. Thank you all. And first, huge shout out to Ethan. If you guys don't follow his Substack newsletter, it's amazing. He's a killer. You got like 10% of the quality in his Substack. But real quick, guys, my name is Jarrod Barnes. I'm the co-founder of ARC. We build infrastructure for agents to learn from experience. The technical term of what we're building is continual learning. It's the ability for agents to actually acquire new skills, to learn and adapt from their environment in real time. We started ARC about 6 months ago. And we started with a fundamental research question, right? We're a team that really prioritizes research. And we said, if we were to build an agentic system that learns like a human, what would that actually look like? What would need to be true in order for that to happen? And so from first principles, we said, let's take a step back and let's think about how do humans actually learn from experience, right? I'm an educator by trade. I spent most of my research career studying educational psychology, particularly in K-12 environments, trying to help learners persist on hard problems. Learner persistence is predominantly rooted in kind of 4 categories of memory, right? And how we actually learn and apply the information that we know, right? A lot of that is through episodic or specific events in your life that you remember and really take with you and internalize. What's interesting is neural networks are actually not so different. And so as we set out on this and we said, okay, well, we have a basic understanding of how humans learn. And what's really interesting is, for those who don't know, the human brain, regardless of how you remember your experience, at the moment you put that experience into application, right, when you actually make decisions, your brain is kind of segmented into 2 forms. One form is called System 1, that's your fast thinking. The other form is called System 2, that's your slow thinking. And what's interesting is we have all of these incredibly powerful reasoning models that can go in the background for now almost 8 hours. We as humans actually spend 95% of our time not reasoning at all. And again, neural networks and AI models are not so different, right? They often hallucinate or think they are right, and act with bias. And so, as we were setting out to solve this problem, really build an AI system that can learn in the same way humans do, we said, well, how do agents learn today? I'm sure many of you have seen this diagram, right? This came from Anthropic back in December, really at the onset of MCP. You have so many things that you can add to LLM context, right? For immediate information and immediate retrieval, right? Tools, short-term memory, databases, right? More and more context. Well, the limitation of this is, at the end of the day, right? A system that learns and builds skill, if you treat memory simply just as factual retrieval, you may or may not actually get accuracy the first time. And the more facts that a model gets in a single turn or a single interaction, that doesn't necessarily mean it's going to compound its experience, right? If you refresh that chat, you're going to lose that context, right? And it's probably going to cost you a lot of tokens, which will add time and latency. Well, then we said, okay, now really we're at this onset of agentic experiences. An agent is able to actually interact with the environment, see that feedback, right, and learn in real time. Well, the challenge there is agents are often stuck in stateless cycles, right? Which means that agent is not able to manually refresh its own memory, right? You're going to spend a lot of time trying to debug reasoning traces. If anyone has ever done LLM evaluations and actually looked at a chain of thought of a model, you're often trying to understand, why did the model do that, right? Where did that come from? That's one of the challenges and failure modes. Then we saw kind of the onset of Claude Code and a lot of these CLI tools that were really sophisticated multi-agent systems, incredibly powerful. However, if anyone has ever built a multi-agent system, there is a significant amount of failure modes. Every new sub-agent, every agent you add to the system, right, you're introducing a potential point of failure, and you're also adding a separate eval burden. You're going to need to eval that specific interaction of a sub-agent, and that's also pretty hard to scale in QA. If you're a product manager, you're probably going to spend a lot of time looking at traces to understand why your sub-agents are interacting that way. And now we're really at this onset of reinforcement learning, right? If anyone has actually trained an agent or trained models using RL or different training algorithms, right? The TLDR is you effectively allow the agent to iterate in a closed classroom, right? I won't get too deep into this. I'll talk more about that in a second. But you need a way for that agent to get feedback, right? Which is a reward, and ultimately update its policy, right? Which is its behavior or its weights. The challenge with that, if anyone here has ever trained model, is RL is really hard. right? It's definitely not easy. There's a lot to configure. You actually have to understand the feedback that you're sending a model, and it requires compute. You're probably going to need to spin up a GPU cluster, right? You can't just do this locally on your device. And so we've kind of reached this plateau where we have incredible intelligence in the models that we're using, but ultimately for individual developers and individual organizations who are building agents, we're actually extending the amount of cost and latency that it takes to build these systems. And so when we said, well, how do we actually adapt this? How can we get an agent to learn from the experience that it gains, embed that as part of its own capability, and then actually take the next step and be more efficient the next time it tackles that same problem? A couple of charts and graphs I'll share just so everyone has an understanding of where model capability is going in the future. This graph is from the Grok 4 release from XAI. For those who may not fully understand this chart, basically what is happening here is the distribution of compute, or the amount of energy that model labs are putting towards training AI models, and the fundamental capabilities is going towards what's called post-training. That post-training is really a way to say, we're going to prioritize a model's episodic memory. We're going to prioritize how that model can learn from experience so that it's able to unlock new capabilities, right? Effectively, we went from GPT 4.5, which was one of the last large pre-trained models. In other words, we're going to scrape the entire internet, and then we're going to shove that into a model, and we're going to call that GPT 4.5, right? Really powerful, very creative, but slow. Didn't have extensive reasoning. Then we had O1, DeepSeek, O3, O4, now a GPT-5, right? That is a distribution heavily focused on post-training, right? And so we're seeing this model capability shift, and more importantly, we're actually seeing the entire training pipeline shift. This came from a new paper that was released earlier this week, or last week, from Meta, on how they're actually training a code world model. To just take away the research jargon there, effectively, they ask the same question. How do you get a model to internalize how it might learn from experience, right? And actually build this capability into the model itself, right? And so again, don't get too distracted by this chart. Basically, what you're seeing here is on the far left, you're seeing pre-training. What that means is we're going to scrape a bunch of text, and we're going to shove text into this pre-trained model, and then about halfway through this training run, we're going to switch that up and not just share a bunch of text and facts. We're actually going to share how a interaction would happen, right? And so you're seeing some agentic reasoning in mid-training, and then post-training much more heavily on these agentic interactions. And so what does that mean? Well, that means models themselves are going to actually have an understanding of the world, right? And know how to respond to events and experiences. And so we're really at this inflection point now from a model capability standpoint where we've gotten to this point of general reasoning, incredible capability, where the reality is the next frontier of models isn't necessarily from just more compute or more pre-training, right? GPT-5 was actually, it was less expensive than GPT 4.5. Which is really interesting. And that tells us right here that the idea of continual learning and acquiring new skills is actually really critical to model capability and where we're going next. So now that we've successfully set the stage, the question is, well, how do we actually make this accessible, right? I just shared big labs are doing this with billions of dollars of compute. What does that actually mean for everyday developers, and how do we do this? Well, we're a fully open source company. We started this work about 6 months ago. So I'm going to walk you through a little bit of just the learnings that we've had in this journey from a research perspective, and then make this real with a practical and tactical demo on a real use case that we found pretty compelling. So the first thing that we did to actually enable this new capability is we separated planning from execution. Right? One of the failure modes of long context agents is oftentimes they get distracted, right? Think about it as a cascade. If you make a mistake on the first step of your plan, all of the steps below that are probably going to be failures, right, as well. And so when you separate planning from execution, you get higher accuracy over long context for more durable accuracy and performance. We see this play out a lot in robotics and in physical AI. Anytime a model is interacting with the real world, you typically have what's called a dual agent system, right? This is from Gemini's new robotics model that they just launched a couple weeks ago, really powerful, but this is also what led to OpenAI and Google DeepMind's progress on the IMO math competition and code competitions. They had basically a dual agent system. And so we said, okay, the first thing we need to do is we actually need to separate this reasoning from execution. Well, if we're going to do that, what is the best way to train a model to simply be a great planner or a great teacher? And so the research question we asked, we said, if you train a model to be a great teacher or a great planner, simply just on hard math questions that are really hard math, can that generalize across domains? The short answer is yes. I'll share here in a second, but we got some really powerful results. And I think the first thing we'll share just from learning and actually training models is the bitter lesson we found is trust the model to actually know enough about the task that it will scale its way to generalization. Meaning, if you actually give a model a foundational, clean, very challenging data set, it will learn to iterate over time, and that can generalize across your specific domain. So we saw this play out, and I'll jump back to this, but we saw this play out on a couple of different benchmarks. The first is actually from Salesforce. They have a benchmark called CRM Arena, which basically is a clone of Salesforce. And they put agents to work within Salesforce to say, how good are you, right? We effectively, at the time, were able to outperform all the state-of-the-art models. And then we did the same on another benchmark from Sierra AI called Tau 2. This benchmark is predominantly how do you actually communicate two ways with another human, right? If a human gives you a really weird input, how do you actually respond to that? This is a common failure mode in agents. And so these are some of the key things that we found along the journey. Now, the second is, okay, great, we've separated teaching and planning from execution. How do you actually get real-time learning? One of the new paradigms that has come out is one of the undervalued things is actually updating a system prompt, and not just updating a system prompt one time, but constantly iterating on that prompt in real time. There's a new methodology called GEPA, which is effectively reflective prompt evolution. I will spare you this diagram, but effectively what you can do is you can take an input. You can allow that input to be the context for this prompt optimizer. The prompt optimizer is then going to create what is called samples or rollouts of multiple system prompts. We're going to evaluate all those different system prompts to see what ultimately performs the best at your task to get you the highest amount of performance at test time or at immediately like inference time when you call that model. That is what allows for real-time adaptation and the ability to get basically as much juice from the squeeze at real time immediately when you get an input to your system. This actually, to date, outperforms even some of the best reinforcement learning algorithms that requires no training, right, and not actually updating the model weights. And so you're seeing a lot of different components here, right, where we've decoupled reasoning from execution. We've now kind of added online adaptation and the ability for the model to update its system prompt. The question then becomes, well, how do you actually allow that model to get the right amount of feedback, right, and understanding and a reward? A reward is simply just a signal for a model. It's a way, no different than if you've ever gotten feedback from a peer or a manager, right? It's a way for a model to adjust its course and course correct based on the reward. Well, you need to design a reward system in order to do that. So as of today, we actually, and shout out to my team who is here, achieved state-of-the-art results on what is called Reward Bench. Reward Bench is simply a way to gauge a model's ability to accurately judge a given outcome, right, that a individual or a user is looking for, right? It's a way for a system to get feedback. And if you really deeply understand model behavior, models are starving for feedback, but how you actually feed them is what really matters. So again, not to get too deep into the diagrams, I know this is a bit more researchy, I'm gonna get to the demo in a second, but really wanna make sure we kind of explain a little bit about how we've built this system. Effectively what we've done, and one of the harder things in reinforcement learning and training models is understanding why a reward model gave a given score. Right? A reward model typically will output a scalar reward, so that's anything between a 0 and a 1. Right? Say your agent executes a task and the reward model says that's a 0.4. The hard question is, well, why is it a 0.4? What led it to making that decision? What we've done then is effectively broken that down and allowed us to get both natural language reasoning of here's the decision and why we have assigned this reward, and then we actually are able to assign it, right? What this means is you're enabling an AI system to get a full feedback loop on every interaction that it makes. So that's pretty deep, but what this actually looks like in combining this together, and this is our system architecture and our operating system. I mentioned, right, we have our reasoning core. This is actually model agnostic, and then that goes to our reward system, right? The reward system takes any given input that you have. I'm gonna show this in a demo. Any given input that you have, turns that into a reward that allows the system to optimize for the best performance in real time, and then all of those interactions, including the outcome, become training data, which you then do what's called offline reinforcement learning and take that real-time behavior change and you turn it into a skill for the model itself. And then we integrate with any specific agent framework. So I know that's a lot of information. I would say that's like pretty indexed on like the machine learning side, so apologies if that was a little dense. But this is really what's happening under the hood with a lot of frontier research, but also B, how you can actually enable continual learning and the ability for models to adapt in real time. And so last thing I'll say before we get to the demo, right, you're saying, hey, this is all good and well, but where does this actually fit? Like, what would I use this for? Well, I think you saw a great example with Ethan at TextQL, right? Really where we've seen the most compelling examples are in, if you look at this 2x2 in distribution of where the observability or the visibility of the outcome, in addition to how dynamic the task is, really matters in that kind of high quadrant. That's where continual learning can ultimately be a really compelling unlock. So those are use cases from incident response to cybersecurity to building a self-healing code base, right? And then we've also seen a lot of interest and demand on behavioral and preference cues. In other words, if you've ever done deep research, right, a way that you do a report may feel different than I do a report. What if the system could actually adapt to your behavior in real time based on that preference and become more and more efficient and more effective and tuned to you immediately, right? That's really the future that we see and future we want to enable. So I've successfully probably talked your ear off. Let's actually see this in action. So if you guys don't know, Claude 4.5 Sonnet dropped earlier today. So Aman, our founding engineer, built an amazing demo, and I blew him up and I said, stop everything, we gotta adjust this. So this is pre-recorded. I'm actually gonna pause this here real quick. Apologies. Quick context. I mentioned incident response as a key use case. What incident response is, if you don't know, is if you're hosting infrastructure and that infrastructure ever goes down, and you're like, why is the website down? Why is our cloud down? Somebody, a human, is on the other side of that, trying to figure out what's happening. Right now, we want to deploy agents to that. It is a very hard task. In the best benchmarks, even GPT-5 only performs 14% accurate on real-time incident response. Very hard problem to solve. Let's see if we can solve it with continual learning. So what we've done is we've actually started a real Kubernetes cluster, which basically means we're hosting a sandbox, right, in the cloud. What you can see here is the first thing we did is we have a teacher and student interaction. This is our initial student, which is Claude 4.5 Sonnet, basically saying like, okay, look, here's my plan. I see the problem, right? This Kubernetes instance is down. Here's the plan that I'm gonna do, right? And now we're having our teacher model review that approach, right? Our teacher model is something we custom trained ourselves. And we're basically saying like, look, your diagnostic approach is solid, but you actually need to adjust your tool usage a little bit, right? You need to be aware of the tool configuration in order to actually solve this problem, right? Our teacher has access to that. So we keep playing here, and I might speed this up a little bit for sake, but basically our system actually, and this is important, actually failed, right? It says false. Long story short, it gave the wrong command. And you know what? That's okay. It was pass at 1, meaning it was the first chance. We're going to try it again. This is the baseline output. So you can see that's just what Claude 4.5 Sonnet does out of the gate. And now we're actually going to have our reward system kick in. We're saying, hey, you know what? You were wrong the first time. So now we need to actually evaluate that response, and we need to give you a reward. You can see here we got 0 for accuracy, right? So now the system knows I was completely wrong, right? We were inaccurate in that. We got 0.5 for helpfulness. We did a good process, and we actually did a really good job with the diagnostic there, right? And so you can see, right, we had a 0.5 reward. So that now the system knows in real time, okay, great, I was wrong. Now I actually need to go back and I need to adjust my behavior, right, based on these rewards that were given to me. So we speed this up a little bit, but you can see we have deep reasoning for each of the rewards. This really matters if you're training models and need to understand how your system is behaving on a high value use case. So for sake of time, I'm just gonna skip a little bit to the end here for sake of time. And let's see. Okay, I'll pause here. So long story short is we completed about 5 different incidents on that. And over time, we were actually able to solve the problem, right? It was kind of a cascading failure. And eventually, we got to a point where we were able to get a positive reward, save our tokens, and ultimately achieve a good result. And so this is just a quick example of what you're able to do. I'll say one last slide, and I'll get off the stage here, of what you're able to do with continual learning. Our framework is fully open source. So if you're interested, please check us out on GitHub. We publish all of our research. So everything I shared, also fully open. And then if you want to try this out, please check out our docs. That's all I got, guys. Thank you so much.